Okay, so in previous class, we show you how to quantitatively describe the flow process and provided you a beautiful equation correlated, uh, which is absolute temperature times the entropy production rate per volume will be equals to the flux of physical entities times uh, the driving force applied on your systems. So following, we provided you three different cases, included the heat flow, electrical flow, and mass transport, three different kinetics process, and that's um, based on these following three examples, we are going to show you that this equation can be used to well describe these three flow process in kinetics. So the first is we have the first one is the heat flow kinetics process. In the beginning, we have two chambers with different temperature, T1 and T2. And because T1 is larger than T2 or higher than T2, so as long as we use the thermal conductor or metal to connect it, chamber 1 and chamber 2, then there must be a flux, heat flux flow through T1 or through chamber 1 toward to chamber 2. And after a serious calculation, and we can see that the net change in entropy, we can calculate the net change in entropy of the system, and also show this heat flow process will cause the entropy production. And in order to calculate the entropy production rate, we also entropy production rate sigma dot can be can be expressed like what? You can the J capital Q is a heat flux times the driving force, which is minus temperature gradient divided by T, and also divided by T, and this is the entropy production rate in this heat flow process, right? And also we give you a second example is the electrical flow process. In the beginning, we have a metal bar. Then we connected this metal bar to a battery, and with the electrical potential gradient V1 and V2, V1 minus V2. And after serious calculation, we also demonstrate that this you can simply calculate entropy production rate per volume in the system by, as long as you know the current density, how much current flow through these materials, and also the electrical field you apply on the system. And then you divide it by T, then you can get the entropy production rate per volume. So this example tells you that the electrical flow will lead the increase of entropy, and you also can quantitatively show us how much entropy, what's the entropy production rate per volume in the system. And the third case actually is a mass flow process, or some people call it a diffusion in solid materials. In the beginning, you have an heavy alloy with varied concentration. That means the concentration gradient at location 1 and location 2. The concentration are different at location 1 and location 2. And as we know, XA1 is larger than XA2, right? So this chemical potential gradient will lead the mass transport. So the driving force here will be the chemical potential gradient. And this is because this demonstrates that the atom A with a higher chemical potential than the atom at location 2. So this mass transport will lead the decrease of total energy of the system. right? And also the atoms with higher chemical potential energy will be pushed toward to the location with lower chemical potential, right? Okay, so this diffusion or mass transport will lead the entropy production. As long as you know the atomic flux and chemical potential gradient and divided by T, then you can calculate the entropy production rate per volume. So I'll give you a quick summary that the rate of entropy change instead of the free energy change can be used to characterize this flow process or irreversible flow process. And we show you that the heat flow, electrical flow, and mass transport will lead the production of entropy in the system. And how much entropy be produced can be calculated by this beautiful equation. As long as you know the flux of intensity and the driving force applied on your system, then you can get entropy production rate per volume. Okay, so next is the last section of this lecture is coupling of forces and flux. How can we deal with if there's two or more driving force applied on these systems? Are there any interference between different forces and different flux? The answer is yes. So there's a term we call it as a coupling coefficient, coupling term between the forces and the flux. And in the second part, we are going to talk about what's the Seebeck and Peltier effect. And at the end of this section, we are going to show you or demonstrate a very famous principle we call it Osaka symmetry. Then we are going to use this Osaka symmetry, this concept for the following slides. So before we show you how to deal with the system coexist with two or more driving force. So you need to have some concept about the entropy production of a system, and you need to have some idea about the system, the surrounding, and which part we are talking about which system you care about. So let's take a look on what's entropy. The thermodynamics defined the entropy is equals to this is like the heat exchange at a reversible process at temperature T. Then you can get the change of entropy. This is in macroscopic definition. And based on the microscopic definition, we also can use the thermodynamic statistics to show you states that the entropy equals to the Boltzmann constant Kb times the log omega. And omega is the numbers of possible combination of the atoms. So some people will say that it's a possible numbers of states. So based on this concept, we will say the change of the entropy in a cell we define is a system you are interested in, can be equals to what? The entropy change from the surroundings. We call it as a ds flux, and plus the change of entropy produced by itself. So we can have some idea, something like that. If we have a cell here, what's the change of the entropy in this cell? Can be expressed like the entropy flux, the flux of entropy from surroundings, and also the production, the entropy production by itself. So this is the S flux is the entropy flux from surroundings. So it's like a redistribution of already available entropy between cells. So it's like some kind of entropy flux from surroundings. The S producer, that means something like the system, like the entropy production rate in this cell or in this system. In previous slide, actually, you calculate lots of like you get the beautiful equation, right? And you can simply calculate entropy production rate of the system. So this is the S production is something like this is how much entropy produced by this cell. Okay, so for the thermodynamic equilibrium state, as we know, the state function do not change with time. And because the state function do not change with time, so the ds, the change of entropy, is equals to 0. And because it's thermodynamic equilibrium state, so as we know, this system do not produce any entropy, so the S production equals to 0. This is equals to 0. This is equals to 0. So there's no any entropy flux from surroundings. This is in thermodynamic equilibrium state. But however, if we are talking about is a steady state flow process, the physical meanings of steady state flow process we mentioned in previous slide is the state function do not change with time. So the partial f partial t equals to 0. Based on this, we know the change of entropy is equals to 0. Right? So this equals to 0. And how about the entropy production in this system? Actually, in the heat flow, electrical flow, and mass transport conditions, in previous slide, we did calculate the entropy production rate per volume in the system, right? So this term, the S production, definitely is positive. And this is 0, this is positive, so the entropy flux from surroundings must be negative. So that gives you some difference between the equilibrium state and steady state flow process. In both cases, the state function do not change over time, and the entropy change is equals to 0. How about when you're talking about the entropy production rate from in this system? In the steady state is positive, but in equilibrium state is 0. And when we talk about the flux, entropy flux from surroundings, in steady state, this is negative. So negative plus positive, then we sum up the final entropy change of the system is equals to 0 in steady state flow process. Okay. So let's move to, now you have some concept about the change of entropy, right? So now we move to the coupling between the forces and the flux. And we're starting from the concept of entropy. As we know, the entropy change can be expressed like the entropy produced in the system and the entropy flux from surroundings. So we also can use this equation and take the partial t to all the atoms. So we just take the partial t here. So you will get the continuity equation of entropy. For example, if we take the partial t is a partial s partial t here, right? And partial s production, partial t is we call the entropy production rate per volume. And also, if you partial this term, partial S flux, partial T, is you can consider as a negative divergence of entropy flux. This is the concept is similar to when we mentioned the continuity equation in previous slide. When we use the atomic flux, we take the divergence of the atomic flux equals to the concentration change over time in the cell or in our system. So it's similar, right? So this is equals to partial S, partial T. So you just substitute, you just replace this concentration as entropy, and the flux here is entropy flux instead of the atomic flux here. So now we get a continuity equation of entropy, and we just simply move the entropy production rate per volume, or just keep here and move the divergence of flux here, this term to the left-handed side, then we got this equation. And starting from this equation and combined with the energy conservation law, or after series deviation, you are going to have the relationship, the equation, link the relationship between the forces and the flux. And the equation is something like this. And you can find the detailed deviation on in the lecture note, page 6 to 7. And we just put more efforts on explain the results and how to use these results in the following slide. So what we get here is the absolute temperature times entropy production rate per volume will be equals to the heat flux divided by T times the negative or minus temperature gradient, and plus the summation term, summation what? The flux times the potential minus potential gradient. If you take a look on here, this is heat flux, and in previous slide we did show you that the driving force for heat flow process is not only the temperature gradient, it's a minus temperature gradient divided by T. This is for the heat flow process, right? And the rest of it for the electrical flow process and also the mass transport process, we can simply sum up into this term, right? Because the atomic flux times the minus chemical potential gradient, and for the electrical flow, it will be the current density times the minus electrical potential gradient. And for the mass transport, is the atomic flux times the minus chemical potential gradient. So it's a flux driving force. So we can just summarize as like this: is a summation of flux times the corresponding driving force. So also can use alpha to substitute I, so it will be like J alpha, F alpha, and make a summation. So if you have one driving force, just J1, F1. If you have two driving force, it will be J1, F1 plus J2, F2. If you have three driving force, it will be J1 times F1, J2 plus J2 times F2 plus J3 times F3. And we also have, then what's the J? Is the flux of entities, right? And when we exist two or more driving force, what's the relationship between this flux and other driving force? So we got a relationship we call it the linear approximation relationship. Can be expressed like this. The J alpha can be equals to summation of numbers of driving force and the relationship between the L alpha beta, F beta. So if beta is alpha, so you will get the equals to L alpha alpha, F alpha, plus beta is beta, so it's L alpha beta plus F beta. So this linear approximation indicate or states that even as we know the flux J alpha directly driven by the driving force F alpha, right? And the relationship we call the direct coefficient. But if our system coexists the other driving force, we call F beta, and this F beta also contribute the flux J alpha the flux of alpha, and how much it contributes to the J alpha. We call it the indirect coefficient L alpha beta. So if you take a look on the physical meeting here, is the beta field driving force F beta also induce a partial flux of alpha entities or quantities through a coupling coefficient L alpha beta. So be precisely and make it clear. So we take an example. Now we have a metal bar, and we apply the electrical field and also the temperature gradient on this metal bar. What's the entropy production rate for this kind of system? Because we do have two driving force apply in this system. So that would be the T times entropy production rate times summation of flux and driving force. So now we have two driving force, so times the corresponding flux. So the small q represents the electrical current density, right? Is the current density, right? FQ is we apply the minus electrical potential gradient, or you can say we apply electrical field. So it's a J small q times F small q plus, because of summation, J capital Q times F capital Q. And the F capital Q here is the temperature gradient. It's the minus temperature gradient divided by T. And the driving force here is the minus electrical potential gradient. As long as we know the flux here, then we just time to FQ and plus this term, then we can get the entropy production rate, right? So now how can we know the JQ and J capital Q? What's the current density and the heat flux? Based on this linear approximation, we can know what the current density goes through this metal bar, directly driven by the electrical field times the L small qq. This is a direct coefficient. And also will be driven by the F capital Q, is a temperature gradient term, times the L small q capital Q, is a coupling coefficient. And this coupling coefficient you can written like this. It means the driving force is a Q capital Q is a F capital Q contribute to the flux of small q is the current density. And this is like something like that. The driving force is the F small q and contribute to the current density, so QQ. So as long as we got this relationship between based on this concept, right? So just practice one more time. J capital Q. Now we have two driving forces, so you put the two driving force here, F capital Q and F small q. And because this is a flux, so directly driven by F capital Q, so this is a direct coefficient, so L capital Q, because driving force is capital Q and contribute on the heat flux. And we also have the electrical field, F small q, exists on the system, and this we call it the direct coefficient is L capital Q small q, because driving force is small q, it contribute to the heat flux. Okay, so based on these two relationships, we can know the J heat flow and current density. Then we just substitute into this equation, and we can know the entropy production rate in this system. Okay. So so first of all, to deal with this kind of problem, first of all, you need to figure out how many driving force exist applied in your system. If there's two driving force, then you can just in order to get the entropy production rate per volume, you just simply sum up the flux driving force and sum up the flux and driving force. And the driving force, because it is you apply on the system, so we know the value for driving force. And the flux, just keep in mind, the current density definitely will be affect not only the electrical field you apply on the system, also will the current density not just affect by the electrical field you apply on the system. It also will be affected by heat flux. Temperature gradient applying on the system. So in the same concept, the heat flow J capital Q not only affected by the temperature gradient you apply on the system, as long as if you apply the electrical field, it will also contribute and affect the amount of heat flux goes through the system, your materials. Okay, so in order to, because you can check the lecture note to, I hope you can check the lecture note to convince you yourself that this equation is real, is believable. It is real. But that's the other approach to show you that this relationship is really works. Let's do the unit check here. So how to do the unit check? So this is temperature times entropy production rate, right? So let's check the unit. Temperature is K, right? The entropy production rate per volume, the unit will be the entropy production. So the entropy production. So entropy is like a ds. So the entropy per, this is the K, right? Temperature. So let me, so the entropy, what's the entropy? The unit for the entropy is the K, because it is the change of the heat flux, a heat flow over at temperature T, right? So it's like this. Then this is entropy production rate, be the time per volume. So you can simply just drop this term. So what you get is the joule per seconds per cubic meter. Okay, so this is the unit we got. And next would be, how about this unit? So the first term is the heat flux. Heat flux, what's a heat flux? The unit for heat flux is the joule per unit time per unit area. So it's the heat flow through your specific area and during the specific time period. So this is a unit for heat flow or heat flux. And the bottom part is the K. And temperature gradient is the K over distance. So you can just simply drop this term. And what you get is the joule per unit time. This is a volume. So identical with the unit we show here. And for the second term is the flux. Flux can be the numbers of atoms passing through your interesting area per unit during the time period T. And this is a potential gradient minus potential gradient. So the unit for potential gradient will be the work divided by gradient is the distance. So if we take a look, area times the distance is a volume, and we left the time here, and the work times the number, so it's the unit also a joule. It's a delta QW. So then the unit are the same. And if you just simply just summarize both of these terms into this one, so we just check the same. the flux of the entity is the number of flux over time period or over the delta t and over the unit area, and the force is then we just times the delta x to the top, also a bottom. So the bottom part will be the delta t and valid. This delta t and valid, and the top part will be what is force times the distance is a joule, right? And number, and use a number to times a joule, is still the joule, right? So after unit check, you can confirm this equation. There's no any problem or any questions. Any questions on this equation? You can just use this one. So next, we are going to give you some samples about the flux times the force, because it's a conjugate force and the flux, right? So for the heat, so the heat flux, J capital Q, and the driving force here would be the minus temperature gradient divided by T. But some people ask about what's the heat flux? Can we measure that? Based on your previous knowledge, we learned that the Fourier's law can help us to know the heat flux, or Fourier's law actually is help us to know the thermal conductivity, and express like the heat flux equals to minus thermal conductivity times the temperature gradient. So as long as I measure the heat flux, then divided by temperature gradient, then I can know the thermal conductivity of this material. So this is Fourier's law tells us. By using this law, we can calculate the thermal conductivity of your interesting materials. For the mass transport case, diffusion process, the flux will be atomic flux. Driving force will be the minus chemical potential gradient. And based on the fixed law, you also know the atomic flux equals to minus mobility, concentration, and chemical potential gradient. And mobility, what's mobility? Mobility is defined by the velocity of moving atom induced by the unit driving force. So you use the unit driving force to push this atom to move, and the velocity, and at this moment, the velocity of this atom, we call it is a mobility. So it's some kind of m, it's a v velocity over force. We call it this as a mobility of this moving atom. So this is a fixed law. And about the charge or electrical flow, for the flux, probably is not the current density. Current density, you need to divide it by the charge, right? So you can know the flux of how many electrical charge flow through your interesting plane in specific time period. But this is a flux, right? And you need to times the driving force. Times driving force actually, as we learned before, driving force can be expressed like the charge, electrical charge times the minus electrical potential gradient. So driving force can be expressed like minus Q electrical potential gradient. So you drop this term out. So commonly we will use the subcurrent density to represent the flux. And the fourth part, we will use the minus electrical potential gradient. And how can we know the electrical current density? Yes, based on the Ohm's law. Ohm's law tells you the current density equals to minus electrical conductivity times the electrical potential gradient, or equals to electrical conductivity times the electrical field. So normally you will measure the current density divided by the electrical field you apply on your materials. Then you can get the electrical conductivity. So you can measure the electrical conductivity of your system. Okay?